This is the Spring Physics 2015 Final Exam Review. Question number 1. Which arrows in the figure below show the correct direction for heat transfer? If you look, at letter A is from 10 degrees Celsius to 10 degrees Celsius. That obviously is incorrect. From 10 degrees to 20 degrees Celsius, that would be going up in temperature. Likewise, for 10 degrees Celsius to 30 degrees Celsius, also going up in temperature. The only one which can possibly be correct is C, where we are going from 30 to 20, because heat always travels downhill, travels from high temperature to low temperature. Question 2. Iron has a specific heat of 448 joules per kilogram degree Celsius, and aluminum has a specific heat of 899 joules per kilogram degree Celsius. If the same heat is added to each metal and they have the same mass, which will have the greatest increase in temperature? We know that Q is equal to, that's a Q, mc delta T. So we can see that delta T is equal to Q divided by mc. If Q is the same in both cases, and M is the same in both cases, then if we want to have a big delta T, we need to have a small value for C. The smallest value for C here is iron. Question 3. Which of the following is an example of heat transfer by convection? The answer to this is water boiling. Anytime we have moving mass, moving matter, which contains a different temperature, we call that convection. The sun radiating energy, that's obviously radiant energy, and a metal spoon is hot to the touch, that's conduction. Ice being frozen, that's a change of phase. We don't know what's going on there. There's not enough information. Number 4, what's needed to change the temperature or to change the phase, like melting of a substance? Well, change the temperature with temperature? No, I don't think so. The correct answer is heat. Heat is not something something has, but it's the transfer of energy from one place to another, and that's what we need in order to heat something up or melt it. Sound cannot travel in outer space because space is too dark. Well, I don't know if that's true. I guess it is some places. Distances are too far. No, can't be that. Sound is a transverse wave. Well, that's not even right, because sound is a longitudinal wave. That only leaves one, and that's there's no medium. So we need to have air or water or a solid or something for a mechanical wave to travel through in order that it'd be able to be transferred. So why did I say air, water, or sound? I meant to say air, water, or the ground, air, water, or a solid. So we need to have something for the medium, for the sound to travel through. So the answer is D. Which of the following is true of a pendulum? The period depends on mass. That is not true. The frequency depends on amplitude. Also not true. This is the only thing that the period of a pendulum depends on. Length and also gravity. It depends on the value for G, which is 9.8 meters per second squared most places. But a pendulum, it only depends on the length. Number 7. A mass vibrates on a spring. If you stretch the spring farther, giving the vibration a greater amplitude, what would change? Well, the first thing we have to recognize is that a mass spring system is affected only by K, the spring constant, and the mass that's on the spring. So, obviously, giving something a greater amplitude is not going to affect the period of oscillation, nor will it affect the frequency, which is, of course, just 1 over the period. So those two things are essentially the same. It can't affect either one of those, so obviously it can be all of the above. So the correct answer would have to be the speed of the mass. What does that really mean? What it means is that even though the period of oscillation, the tick-tock of a pendulum or of a spring, a mass spring system, is going to remain the same. But the speed has to increase because there's greater distance. If we have a really big amplitude or a really small amplitude, that's not drawn very well, but if we have a big or a small amplitude, the distance that's covered has to be greater, which means that the speed has to be greater, and that's the increase in energy. But it has no effect at all on the frequency or the period. The speed of a wave is 10 meters per second, and its frequency is 5 hertz. What's the wavelength? So we know that the velocity of a wave is equal to the frequency times the wavelength. So we can solve for the wavelength itself, and we get the wavelength is equal to the velocity divided by the frequency. So it's equal to 10 meters per second divided by 5 hertz, which is per seconds, and that is 2 meters. The energy of a wave is determined by what? Well, when we look at a generic wave here, which I'm going to attempt to draw, if I have a wave with more energy, looks like that. It's got the same period and the same frequency, same wavelength. What's different about it? And that's this, and that's the amplitude. So the answer is amplitude. Now, some people might be interested to answer frequency, but when we're talking about light, we're talking about the energy of a photon. Okay, that's what we're talking about when we talk about frequency. When we're talking about a mechanical wave like this, we're generally talking about amplitude. A vibrating tuning fork is moving to the right, so someone at point B, what happens to them is they hear a higher frequency. Someone at point D over here would be hearing a lower frequency, and that's the Doppler effect in action. The waves that are over on this side are being compressed. They're close together, so it's a higher frequency, and these are being stretched out because the whole thing is moving to the right. Number 11, the speed of sound in air is 340 meters per second. You see lightning and then hear the thunder 4 seconds later. How far away is the lightning? So velocity is equal to distance divided by time. So distance is equal to velocity times time. We can just substitute in these numbers, 340 meters per second times 4 seconds, and we get 1,360 meters, just a little under a mile. I always learned it growing up that 5 seconds was a mile. The amplitude of the wave shown below is what? Well, the purpose of this question is so that you know the difference between this, and this. This right here is 2 times the amplitude. The amplitude itself is just the distance from the equilibrium point, or the center line there, and the crest, or this distance here to the trough and the equilibrium point. Either one of these two right here is the amplitude. So this is the correct amplitude right here. The second answer would be twice the amplitude. This number, 0.05, is meant to catch you when you look and notice this distance right here, because you see that. And this distance right here is the wavelength. Number 13, in which of the following does energy travel through the particles of a medium? So what we're talking about, particles moving, we're talking about a mechanical wave here. Because what's happening, if I take the end of a rope and I whip it, and let's say I'm standing over here holding on to the rope, and I whip it and it goes to somebody else standing over here, what's happening is the energy is going across from one end to the other. The particles themselves of rope are just going up and down. Okay? So the particles are going up and down and essentially staying in the same spot over time. They're staying in the same spot, but the energy is what's being transmitted from A to B. It's going across like that. So the point of this is to try and equate energy moving with waves. We've seen this in a test before. If we shine yellow light on a photoemissive material, nothing happens. If we want it to emit photoelectrons, what do we have to do? Well, if light obeyed the wave theory, if it was entirely wave-like and not particle-like, then we could shine a much, much brighter wave on there, and a brighter wave would have more energy and would eventually kick out a photon. But that never happens. Instead, the only thing that we can do is to shine a shine a higher frequency of light, like violet or blue or something like that. That's the only way to actually kick out an electron if the other color won't do it. We've seen this guy before too. We're looking at an unknown sample, and we have 4 exemplars down here of bright line spectra from other known elements. So what we want to do is look and see what the unknown sample is made of. If we look at element A, we see that there are these 2 lines right here which do not appear up in the unknown. So since they don't appear in the unknown, element A cannot be one of the elements. Down here, for element B, we see a line here matches a line here matches a line, and a line here matches a line. So it's entirely possible that element B is in our unknown sample. For element C, we see a line here which matches a line here, and we see 2 lines over here that match 2 lines over here, so element C is probably also in our unknown. Element D has 2 lines right here and 2 lines here which do not appear in our unknown sample. So it cannot be element D. So element D cannot be in there. So the correct answer is B and C. Which of the following is true of electromagnetic waves? Red light is faster than blue light. No, they are both the same speed. Violet light is the fastest color. That's meant to trick you because violet light does have the highest frequency and therefore the highest energy, but again, not any faster. Radio waves and light travel at the same speed. This is the correct answer. Radio waves and light waves are the same thing. They're both electromagnetic waves. Okay? So they're going to travel at the same speed. And again, light faster than radio waves? No way, because light and radio waves are the same thing. The only difference is we can see light and we can't see radio. But they're both electromagnetic waves. The image distance for a real image on a screen is the distance from what? Well, here's some background on this question. This question is going to be given to you on a test with a track that's going to look like what we did in the lab. So you're going to have an object over here. Let's say it's a little pine tree. I can't draw a little pine tree there. Oh well, I was going to try. And we have a lens, and the lens is on a little stand, and then we have a screen over here also on a little stand, and then we have our little upside down pine tree image. And the question will label a bunch of things like A, and there'll be a focal point, maybe there'll be some rays going through here like this, and there'll be a focal point, so we'll have like an A and a B and a C and everything like that. The question is asking about the image distance. So the image distance is the distance from the lens to the image. That's DI. Okay? The distance from the object to the lens, that's DO. And then we have up here is F. That's the focal length, the distance to the focal point. And we would also have things like height of the image and height of the object in there as well. But the correct answer is for the image distance, it's the lens to the screen. Number 18, we know an image is real if it appears on a screen. That's the definition of a real image, if it appears on a screen. Could it be larger? Yes. Could it be smaller? Yes. Could it be the same size? Yes. All of those are possible, but that doesn't make it a real image. The real image is if it appears on a screen. The other type of image, by the way, is virtual, and it could be larger, smaller, or the same size as well. We have two polarizing lenses that are shown. One of them is going to only let light through that is polarized in this direction, and the other only lets light through that's polarized in this direction. So obviously we've got an area right here where light can't get through at all. And you can see that these are turned 90 degrees to each other. Light rays entering a convex lens parallel to the principal axis do what? Well, here's a principal axis and here's a convex lens. And let's draw some light rays. So I have light rays coming in, more light rays coming in, more light rays coming in. What do? They all bend in to the focal point. So the focal point is right there. So they converge on a focal point. If this had been a concave lens, then our light coming in would have diverged. Okay, so this would be concave lens, but a convex lens, they're going to converge to a focal point F. Which of the following statements is true of a charged object? A positively charged object has extra electrons. Well, that's not true because electrons have a negative charge. A positively charged object has lost negative charges. That's true. A negatively charged object has lost electrons? No, because then it would be positive. A negatively charged object has gained positive charges. No, if it's negatively charged, it's gained negative charges. And we don't gain positive charges anyway. Positive charges, in general, a positive charge is positive because it's in the nucleus of an atom. And the atoms in a metal ball tend to stay in the metal ball. It's the electrons, the negative charges, that are free to move in and out. So it's generally gain and loss of negative charges in questions like this. A charged object is grounded when it touches a large metal object, or the ground. That's why they call it the ground. When a negatively charged object is grounded, what happens? Well, if the object has a lot of negative charges in it, they want to go somewhere, they want to get away, and when we touch the ground, all of those negative charges go into the ground until they're equally balanced, positives and negatives, in the ball or object. When it has an equal number of both, it's neutral, and that's when it's happiest. So the extra electrons go into the ground. What's the total voltage in the circuit below? Well, in a series circuit, we just add these up, and so the total voltage is equal to 3 plus 9, so the total voltage is equal to 12 volts. We can also sum the resistance, and if we add up these resistors, 2, 6, and 10, we end up with 18 ohms of resistance. We can then calculate the total current. Total current is equal to the voltage divided by the resistance. So we put that in there and we get 12 volts divided by 18 ohms. That's 2/3 of an amp, or 0.67 amps. That's the total current. If we were to replace this 6 ohm resistor with a 4 ohm resistor, what happens? Well, in this case, the total the total resistance goes from our previously calculated 18, it goes down to 16 ohms. So what that means is the current is going to increase. If the current goes up, it goes up everywhere because there's only one path for current, and so the current is the same everywhere in the circuit. So the current is going to increase through all of the resistors. Now, what is true of current I? This diagram I don't like because it is not clear where this I is. If this I is happening after this circuit, then it's the current that's going through here and through here. and we would add those together, and we would get 3 and 4, and we would get 7, which is not an answer choice. My thought is that this current is probably the total current. Okay, so it's the current 2 amps plus 3 amps plus 4 amps. I would have drawn this like this to show that it's the total current, or I'd have given it a subscript like IT. And we add these together and we get 9 amps, and that's the total current, so the correct answer is D. With that same circuit, if I take this 12 ohm resistor and I get rid of it and I replace it with a 16 ohm resistor, it's going to have a higher resistance in this branch. So in this branch, this current is going to go down to 1 point something or other. So it goes down, but what effect does it have on the 8 ohm resistor? It says, how does the current in the 8 ohm resistor change? Well, this 8 ohm resistor is independent. If we add up these voltages, we get 24 volts. And that means this branch has 24 volts, this branch has 24 volts, and this branch has 24 volts. So they all have the same voltage applied. We can do a current calculation, 24 volts divided by 8 ohms, and we get 3 amps. This is unchanged. It's not affected at all by anything in any of the other branches. Each branch we calculate independently, just the way we would do it in our home. If something was plugged in or unplugged to another outlet in the house, that doesn't make the current change everywhere else in the house. So each independent branch is calculated separately, and they have no effect on each other. Magnetic field lines around a straight wire with a current passing through it are what? That letter A should be down on the next line. Straight, parallel, circulating around the wire, or all inside the wire. The right-hand rule, if my thumb is the direction of current flow, so this is current flow, and the arrow is pointed straight up, then the magnetic field lines are my fingertips, and my fingers are curled around the wire like that. So the correct answer is circulating around the wire. Magnetic field lines generally point from what to what. So if I have a bar magnet here with a north and a south, I know that the magnetic field lines connect the north and the south like this. But which direction do the arrows go? And the answer is the arrows go away from north. So they're going away from the north side, and they go to the south side. So the arrows are always pointing towards south. They're pointing away from north, like that. If a magnet is pushed through a coil of wire, what happens? That's current. Current is produced. That's the way generators work. The alternator in your car, they're all made by moving a magnet near a coil of wire to induce a current. A plane mirror, that's just a flat mirror, creates an image, which is what? Well, first of all, is it real or virtual? A plane mirror, a flat mirror, produces a virtual image, not a real image. So we can immediately get rid of B and D. That leaves 2 left. The question is now, is it the same distance behind the mirror, or is it further behind the mirror? The answer is it's the same distance. If I have a plane mirror right here, and I'm standing in front of the mirror like this, my image is standing the same distance away from the mirror on the other side. So this distance here and this distance here are equal to each other. Light always behaves as a wave. Well, sometimes behaves as a photon, sometimes. So it behaves as a wave and a photon. This is the correct answer. So these are not true always. It's that word always that messes that up. Is light faster when it's a photon? No. The photon and the light wave are 2 aspects of the same thing. So there's really no separating the wave and the photon. So the correct answer here is C. What is the role of the strong nuclear force? It causes radioactivity. No, that's the weak force, the weak nuclear force. So it's not that. It causes the protons in the nucleus to repel each other. No, they do that anyway because they're all positive charges and they want to get away from each other. They hate each other. So that's not true. It keeps the electrons around the nucleus. No, the negatives are attracted to the positives, so it's not that. It must be this one. It binds the nucleus together. So the correct answer is D. Energy and mass. So what do we know about energy and mass? We know an equation that we've seen before, E equals mc squared. This is the important part of this, E and m on opposite sides of the equal sign. What that means is that energy and mass can be converted into one another. That's the most important part of this equation, that they can be converted into each other. This c squared just means that there's a whole heck of a lot of energy for a very small amount of mass. Okay? But this equal sign is the big deal here. They can be converted into one another. What is the role of the weak nuclear force? Well, it doesn't bind the nucleus together because we just realized that was the strong nuclear force. Protons repel each other without us having to do anything. They don't like each other because they're all positives. The correct answer is they eject particles from an unstable nucleus. We call that radioactivity. Okay, so that's the correct answer. And that could be an alpha particle, it could be a beta particle, it could be a gamma ray, it could be positrons or neutrons or any kind of particle that it has to emit in order to get the nucleus to be stable. Because nuclei have energy levels just like electrons around the nucleus. And they need to be stable, so they have to spit out a particle sometimes to get stable. A nuclear equation begins like this. What type of equation is this describing? Well, if you'll notice, this right here, uranium-235, that's a pretty big element. If I saw something that looked a little smaller, like this, that's a 1, and it was becoming something like this, this would be fusion. Fusion is two small atoms, two hydrogen atoms, one's deuterium and one's tritium, becoming one helium atom. So we got two becoming one, and then there's an extra neutron here. Up here, I only have one actual atom. This neutron is not an atom all by itself. So what the neutron is doing is splitting that uranium atom into two other smaller atoms. So this is fission. Fusion would be that guy over there. But that right there is fission. And that neutron is serving the part of a bullet hitting an empty bottle. It's going to hit that uranium atom and just split it into pieces. How much mass can be converted to energy in this into an energy equivalent to, this should be 9 times 10 to the 10th joules. So we know the equation E equals mc squared. We're going to rewrite it in a little more convenient form for this equation. M is equal to E over c squared. So now we can solve for M. M is equal to, the energy is 9 times 10 to the 10th joules, divided by 3 times 10 to the 8th meters per second. That's the speed of light. Square that. Now, 3 squared right there is 9. So that makes this equation pretty easy to solve. 9 times 10 to the 9th, 10 to the 10th joules divided by 9 times 10 to the 16th meters squared per second squared. Those are the units, which will go away in just a second. 9 over 9, that's 1, times 10 to the, 10 minus 16 is negative 6. And the units for this are kilograms. So 1 times 10 to the negative 6 kilograms, the answer is B. And for your test, you should be able to solve for M or for E. A device that converts nuclear energy into heat energy is what? That's a nuclear reactor. A nuclear reactor's sole purpose is to convert nuclear energy into heat. a coal-fired power plant or a gas-fired power plant, they burn stuff to boil water, to make steam, to turn a turbine, to turn a generator, to make electricity. A nuclear reactor just replaces the burning stuff. So it boils water, makes steam, and so on. So it just replaces the heat source. Which of the following statements is true of the air molecules in the glass tube in diagram number 2? So we start off here, and we have all of these air particles that are scattered around, and then all of a sudden the air particles are a little more thinly scattered here and much more densely scattered here. So they're scattered here and then dense here. And these are called, where they're dense, these right here are compressions, and then where they're stretched out, those are rarefactions. So the air particles are busily moving back and forth from the left and right, and the wave is clearly moving down this way. The particles are moving in the same direction, so that makes it a longitudinal wave. So most likely what's happening is there's a sound wave propagating along this tube. So the correct answer is A. If the distance between points A and C is 2 meters, so this is 2 meters, what is the wavelength? Well, a full wave is from A to E. This is a full wave, so A to C is just half a wave. So if a half a wave is 2 meters, then a whole wave is 4 meters. Here we have an energy diagram for hydrogen. How much energy would be released if an electron dropped from level 2 down to level 1? So an electron goes from level 2 down to level 1, and in so doing, it has to emit a photon of light. That's my little photon of light coming out. How much energy is released? Well, we can do the math, and we can do the minus 3.40 electron volts minus the 13.6 electron volts, and this is minus a minus, so that's a plus. We end up with 10.2 electron volts, so B is the correct answer. Now, how much energy do you suppose the little photon of light has that gets kicked out of this atom when the electron falls? Well, guess what? It's 10.2 electron volts, and that is going to show up in a bright line spectrum as a very clear band in that spectrum somewhere, and every other transition, so from 3 to 2, or from 4 to 2, or from 5 down to 2, all of these are going to be other little bands somewhere in that bright line spectrum because they're all going to have a very specific, very exact amount of energy. Which transition releases a photon of the greatest energy? Well, the first one is from 1 to 4. There's a problem here, and that is that this is going up. For it to go up in energy level, it means it has to receive a photon, not emit a photon, so it can't possibly be this one. Likewise for this one, going from 2 to 3, that's going up. So they have to receive a photon in order to go up. So giving off a photon requires that they fall down. So letter B goes from 3 down to 1, and letter D goes from 4 down to 1. Which one has the greatest amount of energy change? That's 4 to 1. So the energy from that photon, or from that transition and from that transition, the one that's going to have the greater energy is this little guy right here because it falls further. If an electron is sitting in energy level 3 and a photon comes in and hits it and knocks it loose, how much energy does that photon need to have? So we can come over here and look at energy level 3 and see that it's at negative 1.51 electron volts, so it needs to be more than the negative 1.51. The only one that's more is 2, the 2 electron volts. So if we start with 2 electron volts and we subtract the 1.51 electron volts, we end up with 0.49 electron volts of leftover energy, and that's the kinetic energy that the electron has when it's kicked out. So That little electron is kicked out. It's a photoelectron. So that's what makes your solar calculator work. The sunlight or the light shines on there, and it kicks that electron out, and it has some kinetic energy left over from when it got kicked out, and the amount of kinetic energy that's left over is equal to the 0.49 electron volts. These vocabulary words will be on the test. You'll find them on a separate video file, a separate PowerPoint that should be available on the website shortly.